Hey everybody, today the lesson that we're going to be covering is on tangent lines and equations of circles. There are two videos. In this one, we're going to make sure that you understand what a tangent line is and that you can use the tangent conjecture and the tangent segment conjecture to solve problems about circles, radii, and lines that may or may not be tangent. We're going to give some definitions at the beginning, then have the tangent conjecture and an example, and then the tangent segment conjecture and example. The next video will be about equations of circles. Let's get started with those definitions. So the definition of tangent. A tangent line, a tangent is a line that intersects the circle at exactly one point, called the point of tangency. So in this example that we see off to the right, the circle there, this line is a tangent line because it intersects the circle here at exactly one point. It touches it, is a way to think of it. And the point of tangency is the point where a tangent line intersects a circle. So those are the definitions that we're going to need. So just to think about an example, this couldn't be a tangent line because it would intersect at two different places. And this couldn't be a tangent line because it doesn't intersect anywhere. All right, the tangent conjecture says a line is tangent to a circle. Whoops. If and only if, and mathematicians sometimes use IFF for if and only if, and I'll talk about that in just a moment. The line is perpendicular to a radius of the circle at its endpoint on the circle. So what that's saying is we know that this line M is tangent if this radius, which has its endpoint on the circle, is perpendicular to that line M. Similarly, if we know that this line, this segment that is the radius and has its endpoint on the circle, if it is perpendicular to that line M, then M is a tangent. And that's what the if and only if does. It says we can go both directions. So another way of saying this with this example of the circle is line M is tangent to a circle to circle Q if and only if, and I'm going to use IFF there, M is perpendicular to segment QP. All right, so let's look at an example. In this diagram, segment PT is a radius of the circle, which means that T here is on the circle. And the question is ST tangent to circle P? Now it's important that ST, if it continued on, if it is tangent, that it only touches in one place. So it continuing on is important there. Now, if it is tangent, then we know this is a right angle because we have a radius that intersects with the circle that touches the circle at point T, that's its endpoint. And then ST is the segment that we are curious about being tangent. So now we have a right triangle, and we know that in all right triangles, the Pythagorean theorem must be true for the side lengths. Since side SP is the hypotenuse, we can set up the equation 12 squared plus 35 squared is equal to 37 squared. If that comes out to be true, then it is in fact a right triangle, and that would make segment ST perpendicular to segment TP, which would mean that we do in fact have segment ST tangent to circle P. And when we do 12 squared plus 35 squared, we get 1,369. And when we do 37 squared, we get 1,369. And that is true. So yes, segment ST is tangent to circle P. All right, now let's look at the tangent segment conjecture, which says tangent segments from a common external point are congruent. So in this case, S is the common external point where these tangent segments, SR and ST, come from. So if those are in fact tangents, then segment SR is congruent to segment ST. And if you think about it also, then these radii that come from P to PR and PT, they have to intersect at right angles here as well. And that's not stated in this conjecture, but it's just an important thing to keep in mind. So in this case, another way of thinking about this conjecture in this particular circle is if segment RS and segment TS are tangent segments, then segment RS is congruent to segment TS. That's the conjecture. Now let's have a look at an example. In this example, we are told that RS is tangent to circle C at point S, and we are told that RT is tangent to circle C at point T. Find the value of x. Well, according to the tangent segment conjecture, we know that segment RS must be congruent to segment RT. Since they're congruent, we know that 28 must equal 3x plus 4. And now we can just solve for x. So first we're going to subtract 4 from both sides so that we get that 3x term by itself. And then divide by 3 to get the x term by itself, and we get x equals 8, and that is our value of x. This video was a little bit long. I hope it all made sense. Feel free to respond below, ask some questions, or make some comments. Thank you.